Hello guys, welcome to Learning with Lai. Today's topic is going to be about indices. Indices can be linked with algebra, whereby alphabet symbols are used to represent unknowns, and all that is involved is trying to result to a simpler or simplest form of the initial expression or equation. There are laws in indices when known make arithmetic operation faster and less cumbersome. We can relate indices to this basic arithmetic operation, which we know that 3 raised to power of 2 3 raised to power of 2 is equals to 3 multiplied by 3, or we can also say 3 squared. Let us represent 3 with an alphabet. Imagine letter A. We have this will be a squared is equals to a multiplied by a. Let me use another pen, where a squared, you have the 2 on top is always known as the power or index or exponent, while letter A is actually called the base. So the plural form of index is indices, so that's why we have indices or exponent. Now these laws are, let me write the laws in a different color. These laws are the laws of indices. We have the addition law, whereby we have a raised to power of m multiplied by a raised to power of n. This is equals to m plus n. A raised to power of m divided by a raised to power of n. This is the subtraction law. We have a raised to power of m minus n. A raised to power of 0 is equals to 1. Any number or integer raised to power of 0 is 1. Then a raised to power of minus m is equals to 1 over a raised to power of m. So we have also product of powers. We have fractional indices, and we have the negative power, but we'll look at that in other examples which I'm going to solve. But I'll write the laws against future videos. We have a raised to power of m into bracket n, and this is equals to a raised to power of m multiplied by n. We also have a raised to the power of minus m over n, and this is equals to 1 over a raised to power of m over n. For now, all what we need to do is to take note of these laws. No need to get hasty. We're going to do some examples on each of these laws to give us better insight on these laws. We also have, let me continue the law here. We also have a raised to the power of m over n. This is like the concluding part of this. We're going to have is equals to square root of a, we have n here, all raised to power of m, and we have the final one, a raised to power a over b, equals raised to power of minus m over n, and this is equals to b over a m over n. So now this is the fractional indices, and here now these are the laws. We have how many laws? Let me note them in a red pen. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So we have actually 8 laws, But the fourth, the sixth, seventh, and eighth laws are very similar. We would solve some examples on each law to see how efficient they can be in our calculation. So, where a, m, and n are numbers which can hold certain values or ranges of numbers, let's interpret these laws in terms of numbers. And we need to note that a is not equals to 0. That's one of the conditions we have for some of these laws to be able to occur. Because if we assume that a is 0 in some of these laws, the answer we might get might be undefined. So now, starting with the first law, and since I'm starting with the first law, the way I listed these laws doesn't state that the first law should always be the first in other textbook. So let me go to a newer page with the multiplication law, whereby we have a raised to power of m multiplied by a raised to power of n, and this is equals to a raised to power of m plus n. So let's take, for instance, if we have 10 raised to power of 3 multiplied by 10 raised to power of 2, and this is going to be simply following the format. We're going to have 10 raised to power of 3 plus 2, and our final answer is going to be 10 raised to power of 5. Another, we can also check this. We can check this. So I can write this check. To check it, we can have 10 raised to power of 3 means, from simple arithmetic operation, that will be 10 times 10 times 10 multiplied by 10 raised to power of 2, 10 times 10. And how many tens do we have? That will be 10 in 5 places, and we're going to have 100,000, which is equivalent to 10 raised to power of 5. So it's still going to be the same answer. Another example, whereby still on the multiplication law, whereby we have 2 raised to power of 4 multiplied by 2 raised to power of 3, and following the format of the law, we're going to have 2 raised to power of 4 plus 3, and this is 2 raised to power of 7. If you want to check, let me use a different pen. If you want to check for the second one, this is going to be equals to 2 raised to power of 4 means 2 multiplied by 2 in 4 places multiplied by 2 multiplied by 2 multiplied by 2. Now final answer is going to be 2 raised to power 7, still the same thing as that, because you can see that we have 2 in 7 places. This is 2 raised to power of 7. Now final answer is 128. Now let's go to the next law, a raised to power of m divided by, and this will be the division law. We have it a raised to power of m divided by a raised to power of n, and this is equals to a raised to power of m minus n. And if we're going to take an example on this, we're going to have 3 raised to power of 8 divided by 3 raised to power of 4, and we can see that a is the same. That's why we're having the same numbers there now, and this will be 3 raised to power of 8 minus 4, and our answer is going to be 3 raised to power of 4. And if we want to solve it further, our final answer will be 81, because 3 times 3 times 3 times 3, that's 3 in 4 places. We can also check, whereby we have 3 raised to power of 8. 3 raised to power of 8 is 3 multiplied by 3 in 8 places, that's 2, 3, okay, that's 4, 5, 6, 7, 8, all divided by 3 raised to power of 4, 1, 2, 3, 4, and this will cancel out, this will cancel out, and this will cancel out. So we're left with how many trees? 1, 2, 3, 4. So that's why you can see it's still going to give us the same answer, 3 raised to power 4. Another example we can use on division is, if we have something like this, 28p raised to the power of 6 divided by 7p raised to the power of 3. And all what we do is that we separate the numbers um, to be on one side, and we obey the law of indices on the alphabet, since they are actually the same thing. And this is going to be 28 divided by 7 multiplied by p raised to the power of 6 minus 3, because p divided by p raised to the power of 3, law of indices, that will be p raised to the power of 6 minus 3. And our final answer is going to be 4, because 28 divided by 7, that's 4, p raised to the power of 3. We can also check this by using the long method, and that will be 28 times, in ordinary algebra, 28p is 28 times p, and p raised to the power of 6, p in 6 places, 3, okay, 2, 4, 6, divided by 7 times p times p times p. So we cancel out all the p's, and we're left with, and 7 can divide that, that'll be 4. So we're having only 3 p's left. And you can see that the law of indices make work to be faster and less cumbersome. So now let me go to a newer page. For the next law, we can have the next law is a raised to the power of 0. A raised to the power of 0 is equals to 1, and this is very simple. So anything raised to the power of 0 is 1. But now that's not for the case of a raised to the power a is equals to 0. So that's why in the condition for the laws, I stated that a must not be equals to 0 for all those laws to be held. Because in some cases, when you have 0 raised to the power of 0, some mathematicians tell you that because anything raised to the power of 0 is always 1. Some will tell you that it's undefined, or some will even tell you that it is 0. So this is still a kind of discrepancy in mathematics. So that's why we're not assuming a to be 0, but could be any other integer, maybe negative or positive. So some of the common examples you have is maybe like 15 raised to the power of 0, that's 1. R raised to the power of 0, that's 1. Let us check if this is correct. If we have r raised to the power of 0, and that's the same thing as r raised to the power m minus m. So since we're having m, this could be 5 minus 5, which will still give you 0, 2 minus 2, which is still going to give you 0. And if you are going to obey this now, we can reverse this back to the law of indices, and this will be r raised to the power m, because this is still law of division, but like going back the reverse order, and this is going to be equals to r raised to the power m over r raised to the power m, and they cancel out because they are the same thing, and that's going to be equals to 1. So I'm using different alphabet to try to show that we just need to remember the format of the laws since they are the same things. So now the next law, which is a raised to the power minus m, which is equals to a raised to the power 1 over a raised to the power m. That means when we have a negative power, we take the inverse, and the negative power becomes positive. So that is what is actually happening here. So we can take examples on this, and we have 6 raised to the power minus 2, and this is going to be equals to 1 over 6 raised to the power of 2. And our final answer, if we want to simplify further, that will be 1 over 36. Another example, we have 9 raised to the power of minus 2, and this is going to be 1 over 9 squared. And our final answer is going to be 1 over 81. We can also check, but I'm not going to do that for all the examples. We can also check. To check, we have 6 raised to the power of 2 minus 2 rather is equals to 6 raised to the power of 0 minus 2. And if we look at it, it's still going to give us the same thing. So I'm trying to go back the reverse way. So, and I'll simply write this as 6 raised to the power of 0 minus 2, going back the reverse way, this will be 6 raised to the power of 0 divided by 6 raised to the power of 2. Laws of indices, this will return back to this, and we can simply write this as 6 raised to the power of 0 divided by 6 raised to the power of 2. And any number or integer raised to the power of 0 is always going to be 1, and 6 raised to the power of 2 is 36. So we can say that it is the same answer. Likewise, when we solve 9 raised to the power of minus 2, we're also going to get the same answer. So I have questions to test our understanding with answer. So you can pause the video and try to solve them. So these are the questions here. There are actually 5. So you can pause the video and try to solve them. So after solving them, you can play the video and I have the answer page like few minutes later. So a brief and concise introduction to some of the basic laws of indices, a continuation series to complete this law. Any suggestion and comment can be dropped below, and please click the like button and subscribe. Thank you.